This video deals with Le Chatelier's principle as it relates to equilibrium systems. In everyday language, Le Chatelier's principle states that a system will appear to react in a direction that opposes the change. It will shift to a new equilibrium. However, it tries to alleviate the stress of the original disturbance. When we study a Le Chatelier principle problem, there's going to be 3 steps. We're going to look at the initial equilibrium, the change or the disturbance, and then the reaching of a final new equilibrium. We're going to use Le Chatelier's principle to predict qualitatively how a chemical system will react upon a change or a stress to the system. The first principle is that if we add additional reactants into a chemical system already at an equilibrium, we'll shift the forward reaction. We're going to shift the reaction to the right. And then once a new equilibrium has been reached, it will stop changing. This new equilibrium should have the same equilibrium constant unless the temperature will change. However, the concentration of each reactant and product is now different than the original equilibrium. For example, we're going to look at the production of freon, a CFC or a chlorofluorocarbon, and it's used as a refrigerant in air conditioners and refrigerators. We're going to react carbon tetrachloride with hydrogen fluoride to produce our freon 12 and hydrochloric acid. If we were to improve the yield, we want more freon 12, we're going to increase the amount of reactant, in this case hydrogen fluoride. By increasing the amount of hydrogen fluoride, we shift our equation, or we shift our reaction to the right. And as we mentioned from 2 slides ago, even though a new equilibrium has been reached, the concentration of reactants and products will be different than the original equilibrium. Here we see a concentration of HF initially, and here is our equilibrium concentration of HF. After we increase the amount of HF, the system reacts to the right, it shifts forward so that the amount of HF is reduced. However, at the end of the day, the new concentration of HF is still higher than the old equilibrium value of HF. Shifting the reaction forward is more effective by adding additional HF and not carbon tetrachloride, because carbon tetrachloride is a liquid and its concentration does not change. Just like filling an ice table, we have to consider the concentration of the reactants and products. Therefore, we do not consider liquid in its pure form as well as any solids. Let's now look at the opposite situation. Here, we're going to remove a product. So if a product is removed, the equilibrium should also shift forward, because there is now less product and the system reacts to produce more product to replace the product that was removed from the original equilibrium. If more product is produced, more reactants will also be consumed as well. In this case, back to our freon example, we can shift the reaction forward by removing any or either of the gaseous product. In this diagram, however, we notice a dramatic decrease in HCl, so therefore we know we removed HCl and not CCl2F2. In fact, the amount of CCl2F2 continues to increase because the reaction is shifted forward to produce additional freon gas. And further, because we shift the reaction forward, we're going to consume more of the HF reactants. Therefore, the concentration of the HF will continue to decrease after the equilibrium is disturbed. Le Chatelier's principle is most evident in our body, in our circulatory system. In our circulatory system, or blood, we have hemoglobin binding with oxygen to produce oxyhemoglobin. This reaction is preferred or favored in the forward reaction when the concentration of O2 is high. This will be in the lungs. However, as the blood circulates, the amount of O2 decreases because it diffuses into the cell. Therefore, as the amount of oxygen decreases, the reaction will shift backwards to release additional oxygen from the bloodstream into your cell tissues. Le Chatelier's principle is really just an extension of collision rate theory. When we increase the concentration of the reactant, collisions between the reactants are more frequent, and therefore forward reactions increase. However, as the concentration of the product increases, the products are more likely to collide with each other, and therefore the reverse reaction will happen more often. Eventually, the rate of forward reaction will equal to the rate of the reverse reaction, so therefore a new equilibrium will be reached. On the other hand, if we reduce a substance by removing it, we reduce the reaction rate. So if we reduce the amount of reactants, we reduce the rate of the forward reaction so that the reverse reaction will predominate. And lastly, again, we remind you that if we remove any reagents that are considered pure solids or pure liquids, we will not affect the equilibrium positions because we do not include those into our equilibrium expression considerations. What about temperature? Well, temperature can be considered as a reactant or a product. In an endothermic reaction, energy is part of the reactant. Therefore, if we increase the temperature of a reaction, we're actually really adding more reactants. Therefore, it will shift the reaction forward. However, in an exothermic reaction, energy can be considered as a product. Therefore, if we increase the temperature of the reaction, we're really adding more product. Therefore, we will shift the reaction backwards. And remember, as a general rule, the equilibrium shifts to minimize the change that was induced. Let's look at an example where energy and temperature is involved. If we heat this example here, the reaction of sodium chloride with sulfuric acid, it is an endothermic reaction to yield the hydrogen chloride gas and sodium sulfate. If we heat the reaction, we're actually adding more reactant. Therefore, we're going to shift the reaction forward. We're going to favor the products. Therefore, when the new equilibrium is reached, we will get additional amounts of hydrogen chloride gas. And because you can only get additional hydrogen chloride gas by producing additional sodium sulfate, this line actually on this PowerPoint is incorrect. We will get additional sodium sulfate as well. However, the concentration of sodium sulfate will not change because the concentration is not relevant for entities present as a pure solid, such as sodium sulfate in this case. Let's look at another energy example. Here we have sulfur dioxide reacting with oxygen to yield sulfur trioxide. And our delta H notation tells us it is an exothermic reaction. It will produce energy, it will release energy. So therefore, if we remove energy from our equilibrium, we will shift the reaction forward in order to produce additional products. The last type of change we can affect onto an equilibrium system is to change its pressure or its volume. If we increase the volume of a container, we actually decrease the pressure. Therefore, the system will shift towards the side with a larger total chemical amount, total number of moles of a gaseous product. Let's look at the sulfur dioxide reacting with oxygen example again. Here in our reactants, we have 2 moles of sulfur dioxide gas with our 1 mole of oxygen gas. So on the reactant side, we have 3 moles of a gaseous compound. On the product side, however, we just have 2 moles of a gaseous compound. So therefore, when we increase the volume of our system, we're going to decrease the pressure. And the way that the system responds to a decrease in the pressure is to shift the reaction to generate additional or the greater amount of gas. And because the reactants has 3 moles of gas versus our products where it only has 2 moles, the reaction will shift backwards or to the left to increase the total number of gas moles in our system. On the other hand, if we decrease the volume, we causes an increase in the pressure. So again, if we look at our sulfur dioxide example, we have 3 moles of a gaseous reactant versus 2 moles of a gaseous product. Therefore, if we decrease the volume or increase the pressure, we're going to shift the reaction to the right or forward because the system will respond to the stress by lowering the total number of moles of entities of gas in our equilibrium. The system responds in a way opposite to the stress. If we increase our pressure, the system responds to decrease the pressure. And as a final point, a catalyst does not affect our equilibrium position. It only changes the rate of the reaction. We will get our new equilibrium faster. However, the equilibrium concentration will not be different. To summarize, we have this chart here. It says that if we have an increase in the concentration, the reaction will shift to use up some of the added reactants or products. On the other hand, if we decrease the concentration, it will replace some of the removed reactants or products. For temperature, we can consider energy as a product or a reactant. If we increase the temperature of the system, we're going to shift the reaction so that we absorb some of the added energy. If we decrease the temperature, we're going to shift to release some of the energy. And lastly, for gaseous reactions, we can also change the volume. By increasing the volume or decreasing the pressure, we're going to shift the reaction towards the side with a greater or a larger total amount of gaseous entities. On the other hand, if we decrease the volume or thereby increasing the pressure, we're going to shift the reaction towards the smaller total number of moles of gaseous compounds.